Hello friends, it's a beautiful morning in Kigali. I hope I hope you are doing great wherever you are. Today I want us to proceed from where we stopped in lesson 1 of electric fields. This is electric fields lesson 2. Don't forget this is physics 9702 paper 4 advanced structured equations. So I want us to pick up from where we stopped in lesson 1, and specifically we should now be looking at the electron charge according to Millikan, or in Millikan's experiment. The electron charge according to Millikan. So Millikan in 1912 performed an experiment where he used a uniform electric field to measure the charge of an electron. In his experiment involved the balancing of the gravitational force on a tiny charged sphere or spherical oil droplet by an electric force. In other words, there was balance of the force due to gravity, that is the gravitational force on the oil drop, with the force due to the electric field, that is the force caused by the electric field due to the PD between the two plates. So in his experiment, he tried to ensure that there was a balance between the force due to the gravitational field and the force due to the electric field, so that a spherical droplet would remain stationary in between the plates. So this was Millikan's setup. In his setup, the sphere was actually an oil droplet, which actually became charged by friction as it passed out of the jet of a spray. So oil droplets were forced out through the jet of a spray into this small hole. And as they were passed out, of course, they got charged because of friction. And remember, I have said his aim was just to ensure that the gravitational force on the oil drop, which is due to its mass, is simply balanced by the electric field strength due to the plates. So in his experiment, the two horizontal and parallel metal plates were connected to a source of potential difference, as you can see in this diagram. This arrangement could produce a uniform electric field between the plates. Remember, electric field strength E was given by the potential difference V divided by D. So Millikan realized or knew that the plates would produce a uniform electric field whose field strength would be given by the expression E is equal to V over D. Then this would actually result into an electric force on the oil drop. And of course, from the definition of electric field strength, E is defined as the force acting on a unit charge, the Q. So Millikan was aware that the force due to the electric field strength is going to be the charge on the oil drop multiplied by the electric field strength, which was also the same as the charge multiplied by the PD divided by the separation of the plates. So if D is the distance between the two plates, and if capital V is the potential difference across the plates, the force due to the electric field would be given by that expression. But of course, the electric field could be altered by varying the potential difference across the plates, and the charged droplets were spread through a small hole, as you can see in this diagram, in the top plate of the electric field. So the tendency is for a droplet to fall under its own weight, that is, to fall under due to the gravitational force. So the force due to gravity or due to the gravitational field would be given by the weight of the oil droplet, and this would be given by m times g. So the oil droplets were released at the top of the plate so that they fall under the influence of their own weight. Then, if an observer concentrates on just one droplet and then adjusts the electric field until the weight of the oil droplet itself is balanced by the electric force or the force due to the electric field in the opposite direction, then it would imply that at that point when the oil drop just remains stationary between the plates, the force due to the gravitational field or due to the weight is balancing with the force due to the electric field. And if we equate these two expressions, we would find that mg would be equal to charge times V over D. I want you to note that we are interested in the charge of the oil droplet. So the charge Q would be given as mg times D divided by V. That would be the charge of the oil droplet. Surprisingly, Millikan found out that every time the experiment was carried by a different mass of the oil droplet, the charge Q was always a certain value or an integral multiple of the fundamental quantum of charge E. Note that E had already been established to be equal to 1.6 times 10 power negative 19 coulombs. This experiment showed that for every oil drop which Millikan concentrated on, the charge Q was always an integer multiplied by the fundamental quantity E. In other words, an integral multiple of E. Note that E had already been established to be the elementary charge. So, Millikan concluded that the charge was always an integral multiple of a fundamental quantum of charge E, which we call the elementary charge. This is actually the smallest charge we can have. It is the fundamental charge that we can have. That means all other magnitudes of charges should be multiples of this value. And what conclusions could we make from this experiment? From this experiment, we could therefore conclude that charge is actually taking up discrete amounts. Charge takes up specific values which are integral multiples of the fundamental charge E. Charge does not take on any random values. Charge takes on specific values which are multiples of E. If this was quantum physics, we would simply say charge is therefore quantized. So what we mean by charge being quantized is that charge takes on certain values which are multiples of the elementary charge. So we simply say charge is basically quantized. So in summary, this is all that I have been saying. All that being said, we have now noticed that Millikan found out that charge was always an integral multiple of the fundamental quantity, which is E, and that is 1.6 times 10 power negative 19 coulombs. Remember, we have seen that the weight mg is equal to the force due to electric field, which is charge, times E, which is the same as charge, times V over D. And we found out that Q would be mg times D divided by V. And every time a calculation was taken, Millikan found out that the charge Q was always an integral multiple of E. And E had already been established to be 1.6 times 10 power negative 19 coulombs. So we say that charge takes on specific or discrete values. The fundamental charge was described to the charge of the electron, and the experimental result that the charge on the oil droplets seems to be only an integral multiple of E means that charge is quantized. So the next time when somebody talks about charge being quantized is referring to charge taking on values which are multiples of 1.6 times 10 power negative 19 coulombs. Example. A negatively charged polystyrene sphere of mass 3.3 times 10 power negative 15 kilograms is held at rest between two parallel plates 5.0 millimeters when the potential difference between them is 170 volts. How many excess charges, excess electrons are on the sphere? How many excess electrons are on the sphere? Note that it is held at rest. That means the force due to the weight of the sphere should be equal to the force due to the electric field. That means M times G should be equal to the charge times electric field strength. That means since they have given us V, this should be the same as charge. E is V over D. So we want to find Q. So Q is going to be M times G, then times D over V. I'm making Q the subject from this expression. So if we try to substitute quantities here, it is a negatively charged polystyrene sphere of mass 3.3. So this is 3.3 times 10 power negative 15, assuming G is 9.81. The distance between the plates is 5.0 times 10 power negative 3, divided by the PD, which is 170. When I press my calculator, I find that Q is 9.5 times 10 power negative 19 coulombs. That is the value of Q. Now that is the total charge of the polystyrene sphere. But how many excess electrons do we have? We know that total charge should be equal to the number of electrons times the charge of an electron, because charge takes on values which are multiples of the elementary charge. That means the number of electrons is going to be equal to Q, which is 9.5 times 10 power negative 19 divided by 1.6 times 10 power negative 19, because the elementary charge is 1.6 times 10 power negative 19. When we press our calculator, we have 5.9 excess electrons. But because we cannot have 0.9 excess electrons, we shall round off this to 6 excess electrons. So the number of excess electrons is approximately 6. So the discrepancy must be due to experimental inaccuracies or to rounding off errors. We have been working to only two significant figures, as you can see. But maybe if we could work to more significant figures, we would get n as a perfect whole number. The discrepancy, why it was not exactly 6, is because of experimental inaccuracies, or this could be systematic, not necessarily systematic error, it could be random error, and so on and so forth. Therefore, we can round off this to the nearest whole number so that n will be equal to 6. So there are 6 excess electrons. I want you to note from the previous demonstration that actually it makes sense that if the electron, if the oil droplet is at rest between the plates, it is only because it is negatively charged. Because if the upper plate is positive and the bottom plate is negative, first of all, we are aware that the weight acts vertically downwards. Therefore, the force to balance the weight must be acting vertically upwards. It is only a negatively charged particle which experiences a force in the opposite direction to the electric field. Note that the field lines originate from high potential to low potential. So this charge, the oil drop, cannot be positively charged, yet it is experiencing a force in the opposite direction to the field. Therefore, we conclude that the oil drop must be negatively charged. If the force exerted to balance the weight is in the opposite direction to the field. If the oil drop was positively charged, the force due to the electric field will be downwards. Therefore, unless we reverse the plates so that the bottom plate is positive and the upper plate is negative, we cannot have a situation where the oil drop remains at rest between the plates. Okay, so we have seen that the excess number of electrons is actually 6. The excess number of electrons is actually 6. Example number 2, which is a continuation of the first example. The charged sphere in the example above suddenly loses 1 excess electrons. It suddenly loses 1 excess electrons. That means the new charge is going to be 5 times E. That is the new charge. 5 times E, because it has lost 1 excess electron. The PD has remained the same as before. Remember, V was 170 volts. Describe the initial motion of the sphere. I want you to recall that initially we saw that it was remaining at rest. Initially, the force due to the electric field was equal to the force due to the gravitational field or the weight. But now that it has lost 1 electron, note that Fe depends on the charge times the electric field strength, which depends on Q times V over D. If V has remained the same and D has remained the same, it means E has remained the same, but Q has reduced. Because Q has reduced, it means the force due to the electric field has also reduced. Therefore, the new condition will be that now the force due to gravity is no longer the same as the force due to the electric field. In fact, the force due to gravity is now greater than the force due to the electric field. And because gravity is downwards, then they said describe the initial motion of the sphere, so it will move downwards. It will move downwards because the resultant force on it is downwards. Then at what acceleration will it move? At what acceleration will it move? So by Newton's second law, this was part A. Part B, by Newton's second law, the resultant force F is given by mass times acceleration, where the mass, where we know the mass, of course, from the previous example. The mass was 3.3 times 10 power negative 15. 3.3 times 10 power negative 15. That was the mass. But to find the acceleration, we need the resultant force, where the resultant force will be the force due to gravity minus the force due to the electric field. So it means the acceleration A will be equal to force due to gravity, which is the mass, times gravity, field strength, minus the force due to the electric field, which is actually charge, times V over D. Then divide this by this mass here. This is divided by M. So we can now substitute. The mass is 3.3 times 10 power negative 15 times 9.81 minus, the charge is now 5e, which is 5 times 1.6 times 10 power negative 19, then times v, which is 170. This is divided by, of course, here there is a d here, so I'll say divide by d, which d was 5 times 10 power negative 3. Then divide by m, which is 3.3 times 10 power negative 15. So we press our calculator. So when you press your calculator, you should be able to get the acceleration at this point. I will not press the calculator for you. You can press it and find the acceleration at that point. So that will be the acceleration at that point. Okay. Next, let us now look at the motion. Let us look at the motion uh, of electric charges in an electric field or in a uniform electric field. How do electric charges behave in a uniform electric field? So a charged particle at rest, even though it is moving along the direction of an electric field, it will still experience an electric force. Now, the direction of the force will automatically depend on the sign. The direction of the force will depend on the sign of the charge. We don't expect a positive charge to move in the same direction as a negative charge. So the direction of the force will depend on the sign of the charge. And a positive charge, this is plus Q is referring to a positive charge. A positive charge is expected to be accelerated in the direction of the electric field. That is, a positive charge moves in the same direction as the field lines that we are considering here. A positive charge moves in the same direction as the field lines. But of course, a negative charge moves in the opposite direction or is accelerated in the opposite direction to the electric field. And note that the acceleration and the force are always in the same direction. Therefore, in a uniform electric field, we should always note that a positive charge will experience a force in the same direction as the field, that is, from high potential pointing to lower potential. Yet a negative charge will experience a resultant force in the opposite direction, that is, the force points in the opposite direction to the field. That is, this time the force will point from low potential to high potential. So I am saying that for a uniform field, the force and thus the acceleration are constant, because after all, we now know that force is equal to charge times E. If E is constant for a uniform field, then force is constant. And since force is mass times acceleration, if the force is constant, also the acceleration will be constant. And if that is true, then the equations of motion that we employed in uniformly accelerated motion could be very important at this point. The equations of uniformly accelerated motion could be important at this point. So we shall use them, and these may include V equals to U plus AT, V squared equals to U squared plus 2AS, and S equals to UT plus a half AT squared. We saw these equations in AS, and since the acceleration is constant in a uniform field, we shall also employ them. Let us see. Handling calculations. Let's consider uniform electric field E produced by potential V across two horizontal and parallel metal plates separated by a distance d as shown here. Remember, we have already seen that the electric field strength is equal to force acting on a unit charge. We have also seen that E is equal to V over D. This implies we should be able to play around with these two equations to come up with several expressions that we may need later on. For example, if I want acceleration, then this will be equal to ma divided by the charge, which implies that the acceleration can be given as q times e over m. The acceleration can be given as q times e over m. If I consider this expression here, you will realize that the acceleration in this case could be given as q v over m times d. Note that this is capital V, which is electric field, I mean potential difference between the plates. So we shall need such concepts in our calculations. We shall need to play around with these concepts in our calculations. Example. Suppose we have a positive charge which is released in a uniform electric field, and its mass is given as that. Number one, we may want to find the force it experiences. We may want to find the electric field strength. We may want to find the acceleration. We may want to find the work done to move from, say, point A to point B. So let us begin with maybe the electric field strength. That is E. Part A, let's find electric field strength. By definition, E is equal to force per unit charge, which is the same as V over D. This is at zero potential, the other one is at 1000 volts. So this will be potential difference is 1000 divided by the separation of the two plates is 0.1. And when you divide, I think this gives you 10,000. That is volts per meter. That will be the electric field strength. If I want the force acting on the charge placed in the field, that is part B. I want the force. The force is equal to Q times electric field strength. They have given us Q here, so we can say 10 times 10 power negative 6 times the electric field strength, which is 10,000. And when you press your calculator here, I think this gives you 0, 10 microcoulombs. I think this gives you 0.1 newtons. So that is 0.1 newtons if you want the force. If you want the acceleration, let's say in part C, if you want the acceleration, we know that resultant force is mass times acceleration. So the acceleration is going to be the force, which is 0.1 divided by the mass. The mass is 0.1 times 10 power negative 3 to change to kilograms. And this gives you 1000 meters per second squared. So the acceleration of the charge is 1000 meters per second squared. So if the charge was just released from rest at point A, we may want to find the velocity at point B. So that is my part D. I may want the velocity at point B, here at point B. So here at rest, initial velocity is 0. So I borrow the equations of motion because it is a uniform field. Electric field strength is constant, the force is constant, the acceleration is constant. So using V squared equals to U squared plus 2AS. This part becomes 0 because it was released from rest. Therefore, V squared is going to be equal to U squared, which is 0, plus 2 times acceleration, which is constant 1000, times the displacement, which is between A and B, which is 0.05. So this gives me, when I find a square root, it gives me V. And because this is 2000 times that, which is 100, finding the square root, that gives me 10 meters per second. So that is the speed with which it reaches point B. I may want to find the work done to move from A to B. Work done, that is part E. Work done, of course, work done is force times distance, but remember force is Q times E, where E is V over D. And when you substitute, you'll find, okay, that is Q times E, then times D. Again, this would be Q, where there is E, I put capital V over D, again times D. So you realize that work done is simply charge times potential difference, which is going to be 10 times 10 power negative 6, then times the PD, which is actually 1000. PD is 1000, and that gives you the work done will be actually 1000 times 1000 times 10 power, I think this is 0.01 joules. That is the work done. You realize that if I equate this work done to a half mv squared, if I equate the work done to a half, if I equate this work done to move from okay, this is the work done by the velocity. So we can also calculate the velocity at point B using the kinetic energy, say at B. If the charge was released at rest, then we can equate a half mv squared to actually this work done, and we would be able to find the kinetic, I mean the speed as that. So if I equate this to a half mv squared, a half mv squared, so we multiply this by 2, but also note that the distance here is 0.05. So you must think about that when you are calculating the work done. So you just equate the work done to a half mv squared, and you'll be able to find the same speed. Let's try this and see. So from kinetic energy, a half mv squared is going to be equal to the charge times the PD. So this is going to be equal to, the charge is, this will be 10 times 10 power negative 6, then times the PD, which is 1000. Then this is going to be divided by the mass. I'm trying to make V the subject. Divide this by the mass, which mass is actually, okay, so we said kinetic energy is equal to charge, but I think this will delay us because I have again to, let me just use a simple expression. So the work done by the field on the charge is going to be equal to the gain in kinetic energy. Note that we are only considering A to B. I would just equate a half mv squared to qv if I'm finding the speed with which it reaches here, if it was released from this point. But since it is just from A to B, I will just say that kinetic energy, which is a half mv squared, is equal to the gain. The gain in kinetic energy is equal to the work done. I will simply use the force times distance. If I have this as the force, I will equate this to 0.1 because the force remains constant, but the distance from A to B is 0.05. So it means that V speed, that is, will be equal to twice times 0.1 times 0.05, then divide by the mass, which is 1 times 10 power negative 3, Then find the square root. I hope it gives you the same value, 10 meters per second. As simple as that. Okay, let's progress. Let's just progress to another example. So this is supposed to be a self-check example, but I'll try to give a hint and go through it as people gain confidence in electric fields. So force, a particle, this mass, charge, which is that one, is placed near the top plate of an electric field similar to the one shown below. The potential difference across the plates is 600 and the separation is 12. Determine the force on the particle. So by definition, we know that electric field strength, E, is defined as the force acting on a unit positive charge, which is V over D. This implies that the force is going to be charge times V over D. When I substitute, the charge is 3.2 times 10 power negative 19, then times V, which is 600, divided by D, sorry, V is 600, not 6,000, divided by D, which is 12, times 10 power negative 3. I press my calculator. So this is 1.6 times 10 power negative 14 newtons. Part B, the acceleration of the particle. In part B, we want acceleration. We know that force is equal to mass times acceleration. We have already the force, we don't need to waste time. So it means the acceleration will simply be the force, 1.6 times 10 power negative 14, divided by the mass, which mass is 6.7 times 10 power negative 27. So this is giving me 2.4 times 10 power 12 meters per second meters per second squared as the acceleration. Then part C, we want to find the speed of the particle when it reaches the bottom plate. So you have two options. You can equate kinetic energy to work done, or you can use equations of motion. So I hope I should use, because the PD, it is leaving one plate to another plate, the work done is just charge times the PD. So I can say a half mv squared is equal to charge times PD, which means the speed v is going to be the square root of 2 times the charge, which is 3.2 times 10 power negative 19, then times accelerating PD, which is 600, then divide by the mass, which is 6.7 times 10 power negative 27. I hope this gives you. Press and check. So this gives us 2.4 times 10 power 5 meters per second. Alternatively, I'll do the alternative here. You would have used the equations of motion. V squared is equal to U squared plus 2AS. It is released from rest. U is 0. So V is going to be the square root of 2 times the acceleration which you have obtained here, 2.4 times 10 power 12, then times the displacement, that is the separation of the plates, 12 times 10 power negative 3, and I guess it gives you the same value as before. Okay, so self-check, I think we can now solve this self-check. Calculate the speed of an electron accelerated from rest initial velocity is 0, through a distance of 40 millimeters by a uniform electric field of 3.0 times 10 power 3 newtons per coulomb. We want the speed of an electron accelerated from rest through that distance by a uniform electric field of 3.0 times 10 power 3 newtons per coulomb. Maybe to give people a hint on that question, have all the principles at your fingertips. Have all the principles at your fingertips. When you have them, then it becomes very easy. So it is an electron. So we know the charge of the electron. The work done is going to be called the gain in kinetic energy. The work done, which is charge times accelerating PD, is the same as the gain in kinetic energy, which is a half mv squared. You check if that can give you the speed. If that can give you the speed, you have the charge, you don't have the accelerating PD. You know the mass of an electron, you want to find the V. Also, remember that electric field strength E is given as V over D. Electric field strength is given as V over D. So E is also V over D. And also note that the force F is equal to charge times electric field strength. And also you notice that the work done is equal to the force times the distance. So you can just play around with these equations and know which one should I choose for what. So since the work done is the gain in kinetic energy, I think this is more direct. So this will be a half mv squared. The force is Q times E. So I will say Q times E times D is equal to a half mv squared. This is more direct. So it means V is going to be 2 times the charge, 1.6, times 10 power negative 19, times the electric field strength, which is 3.0 times 10 power 3, then divide by the mass of an electron, which is 9.11 times 10 power negative 31, then it is under the square root. I hope it should be able to give you 6.5 times 10 power 6 meters per second. You can try to check and see. Number 3, an electron starts from rest at the bottom plate in a field similar to that in the figure. That is in the example above that we have done. The potential difference across the plates is 1600. The separation, that is D, 15 millimeters. Calculate the time taken for the electron to reach the top plate. Calculate the time taken for the electron to reach the top plate. So here you can press your calculator and verify that V is 6.5 times 10 power 6 meters per second. An electron starts from rest. Initial velocity is 0 at the bottom plate. The potential difference across the plates is 1600, that is capital V. The separation of the plates is 15 millimeters, that is D. Calculate the time taken for the electron to reach the top plate. So let me rub off this, and I use the same space to give people a glimpse into this. So one, we have V and we have D. We know that is an electron starting from rest. Initial velocity is 0. So you can check the equations of motion. But what is very important is to have the acceleration. So from mass times acceleration is equal to charge times electric field strength, which is charge times V over D. I am going to find the acceleration as Q, which is 1.6 times 10 power negative 19 times V, which is 1600, divide by D, which is 15 times 10 power negative 3, then divide by M, which is 9.11 times 10 power negative 31. This gives me the acceleration. Now it starts from rest. I may use V is equal to, no, not V, I will use an expression which has distance, which has displacement. So I'll use S is equal to UT plus a half AT squared. This part will be 0 because it starts from rest. But the displacement is going to move is this, so I will say 15 times 10 power negative 3 is equal to a half. The acceleration, we have got it here, so this will be times 1.6 times 10 power negative 19 times 1600 divide by 15 times 10 power negative 3, then times 9.11 times 10 power negative 31, then times t squared. So you cross multiply, make t squared the subject, find the square root. I'll just press my calculator to find the t from this point. So my calculator is giving me 1.26 times 10 power negative 9 seconds. 1.26 times 10 power negative 9 seconds, not meters per second. 1.26 times 10 power negative 9 seconds. You can verify again and see if that is true. Okay, number 4. For the electron in question 3, calculate the work done by the field on the electron. Work done, that is very simple. Charge times PD. Work done is charge times PD. The charge is the charge of an electron, then times the PD, which is 1600. It should be able to give you that. The work done is equal to the gain in kinetic energy, so the answer is the same as that. The speed of the electron, you can equate to work done to a half mv squared. In other words, you can say qv is equal to a half mv squared. You find the small v. Alternatively, you can use the equations of motion. Now that you have the displacement, you know you can also use v squared is equal to u squared plus 2as. If you have the acceleration here, this would give you the speed. As simple as that. And I expect that you should be able to get this as the speed. You can verify that. Next, an electron emitted from a hot cathode in an evacuated tube is accelerated by a PD of 1.0 times 10 power 3 volts. Calculate the kinetic energy and the speed required by the electron. The work done by the PD is equal to the gain in kinetic energy. So our work done is equal to Q times V, which is the gain in kinetic energy. So you have Q, it is an electron. You have the accelerating PD, that is the gain, the kinetic energy. Then if I want the speed, I just again equate this to a half mv squared. I just get the kinetic energy obtained, I equate to a half mv squared. You should be able to get that speed. Calculate the acceleration of an electron in a television tube where the electric field strength is this. Acceleration. The charge of an electron is given, the electron mass is given. We want the acceleration. Electric field strength is force over charge. which is mass times acceleration over charge. So the acceleration is going to be equal to the charge times electric field strength over the mass. All that is very important is to change this from volts per centimeter to volts per meter. If 1 centimeter is corresponding to 50,000 volts, remember 1 centimeter is 1 over 100 meters. So 1 over 100 meters corresponds to 50,000 volts. How about 1 meter? That would be 50,000 times 100 volts. So it means changing this from volts per centimeter to volts per meter, we multiply by 100. So you will have 1.6 times 10 power negative 19 multiplied by E, which is 50,000 times 100 divided by the mass, which is 9.11 times 10 power negative 31. This should be able to give you that acceleration in meters per second squared. Okay, let us also look at the motion of a particle, a charged particle, which is now entering at with an initial velocity perpendicular. We have seen previously that the particle has been moving along the field, either in the same direction as the field or in the opposite direction to the field. Let us look at the path of a charge with an initial speed normal to a uniform electric field. Let us look at the path of a charge with an initial speed perpendicular to a uniform electric field. So suppose a beam of electrons enters horizontally in the space between two parallel plates. The question is, how will the beam move? Note that if a charged particle which is positive enters an electric field with a velocity say v at 90 degrees to the direction of the field, the particle experiences a force at 90 degrees at right angles to its initial direction. If the field is vertical and the initial direction is horizontal, the particle will follow a certain path which is said to be parabolic. It actually follows a parabola. This is exactly what we are talking about. If we consider a particle that is charged, in this case, if the particle is negatively charged, it will move in a parabolic path which is towards the positive plate, because as soon as it enters the field, it experiences a force which is perpendicular. This is the force due to the electric field. This force acts normal to the direction of the field, and it always acts in the same direction. So this force will cause the particle to move at a certain path, which we call a parabolic path. If the particle was positively charged, here I was considering a beam of electrons. If this was a stream of positrons, yes, a stream of positrons, then the path would be parabolic towards the negative plate, because the force on positively charged particles is in the same direction as the what? As the electric field. Let's try to analyze the motion of this particle in this field as we wind up lesson 2. So the analysis of the motion is similar to that of a particle of mass say m moving in a gravitational field which is uniform, with say a uniform velocity in one direction and a uniform acceleration in a perpendicular direction. That is what we described in projectiles. So because the field is in one direction, it is acting vertical, just like gravity was acting vertical. When a particle enters horizontally, it experiences a force in the vertical but not in the horizontal. There is no resultant force in the horizontal. Therefore, when we are treating this, we have that in mind, that the acceleration in the horizontal is zero, simply because there is no resultant force in the horizontal. But there is an acceleration in the vertical because the force is now acting vertically. So let us consider an electron, just a single electron whose mass is initially m. which is moving horizontally with a velocity v initially before it enters the field. And then it enters the field between two parallel plates, say P and Q. Let us consider capital V to be the potential difference between the plates, and we are going to consider small d to be the distance between the plates. From those two quantities, we know that the electric field strength E is going to be defined as capital V over D. And also, we know that the force due to the electric field acting on the electron, the force due to the electric field on the electron will be the charge E times the accelerating PD. Not accelerating PD, it will be the charge E times the electric field strength. So it is small e times capital E, or charge times electric field strength. And this implies we can also think about this force as being E times V over D. Now, we are going to treat this the same way we treat projectiles, or we treated projectiles in AS, because this is a uniform field. The force is constant, the acceleration is constant, so the equations of motion can be used. If we initially consider horizontal motion, considering horizontal motion, acceleration in the horizontal is zero because the resultant force in the horizontal is zero. There is no force acting in the horizontal. And if that is true, the final velocity in the horizontal, when it emerges, say, at this point here, of course, it has a velocity in the horizontal and a velocity in the vertical at this point. The resultant velocity is the velocity along this line. So let's say this is Vx, and let's say this is Vy. So when it emerges, Vx is the same as the initial velocity here, is the same as V because there was no acceleration in the horizontal. I'm still considering horizontal motion, and if I consider horizontal motion and I try to use S is equal to ut plus a half at squared. S in the horizontal, initial velocity in the horizontal, acceleration in the horizontal, which is zero. S in the horizontal is now going to be the length of the plates. We are considering when it is emerging from the plates. So this will be L. Initial velocity in the horizontal is V times the time it takes, which is T, plus zero because the acceleration in the horizontal is zero. So we are trying to show that the time it spends between the plates is going to be L divided by the velocity before it entered the plates. The time between the plates is simply L divided by V from this expression here. Okay, since time is a vector quantity, the time taken in the horizontal is the same as the time, since time is a scalar quantity, the time in the horizontal is the same as the time in the vertical, as it was with the projectile motion. So that one we don't mind about it. Now let us consider vertical motion. Here I consider the horizontal motion to find the time between the plates. If I consider vertical motion, because the particle entered initially horizontally, it means initial velocity in the horizontal was zero. Initial velocity in the horizontal was zero. Of course, there is a final velocity Vy, which can be Uy plus acceleration in the y times t. And since initial velocity in the horizontal was zero, so the velocity with which it emerges in the vertical is simply acceleration in the y times t. And if I can find the acceleration in the y, after all, I already know that the force F is equal to the mass times acceleration, which will be now the acceleration in the y, because there is a force in the y. This will be equal to, of course, the force has been given as ev over d. So this will be E times v over d. That means acceleration in the y is going to be E times v divided by m times d. That means the velocity in the y can always be looked at as E times v over m times d, then times t, which t is L over v. So that is times L over small v. That can be the velocity in the y. I may want, or we may want the vertical displacement y as the electron emerges from the field. The vertical displacement y as the electron emerges from the field. It means we are still going to consider vertical motion. So this time we shall use S is equal to ut plus a half at squared. This will be S in the vertical, initial velocity in the vertical, acceleration in the vertical. Note that this part here becomes 0 because initial velocity in the vertical was 0. The electron was entering horizontally. So displacement in the vertical is going to be y equaling to a half times acceleration in the vertical, which is E times V over md, then times t, which is L over V, so this will be L over V, and this can be squared. This expression can give us the vertical displacement as it emerges from the field. If you're a pure mathematician, you realize that this is the same as y equals to E times V over 2 mdv squared times L squared. And this is similar to y is equal to ax squared, which is an equation of a parabola. So we say that the path followed by particles in an electric field is parabolic. Of course, for our curriculum, we shall not go into the details of it being parabolic. However, we shall always be using the equations of motion to solve some of those um, those questions as required. By the way, you might also be interested in finding the vertical displacement on the screen. I want you to note, first of all, that as the electron emerges, it continues in a straight line if the surrounding area after the plates is a vacuum. It continues in a straight line with its velocity that it has obtained when it is just emerging. I also want you to realize that the resultant velocity Vr at this point is the square root of Vx squared plus Vy squared, as we saw in projectiles. Okay, so we have noted y1, I will call this one vertical displacement y1 when it is just emerging as say E V over 2m dv squared times L squared. I will call that y1. And so we have seen that the vertical displacement here, y, which I'm calling y1, was E times V divided by 2m d v squared times L squared. Note that it could also be in terms of E because V over D is E, so it doesn't give any difference. But we may want the capital D. So if I draw a horizontal line here, this portion is for y1. That means it leaves a portion for y2. So at this point where it emerges, it has a velocity in the vertical, it has a velocity in the horizontal. This is Vx, this is Vy. And this angle here, theta, is the same as this angle here. If the distance between the plates and the screen is L, you will realize that tan of theta is going to be opposite, which is y2, over adjacent, which is this distance L. But at the same time, using Vx and Vy, tan theta is going to be adjacent opposite over adjacent. That is Vy over Vx, which implies that y2 could be also Vy over Vx times L. Now this is capital L to distinguish it from the small l. So it means I can find capital D as the sum of y1 plus y2, where I sum up this to that to get the total vertical displacement on the screen. I want people to note I want people to note that at this point here, tan theta is vertical, is Vy in the vertical over Vx in the vertical. We saw that in projectiles. But the resultant velocity at this point here, Vr, which I'm calling V resultant, is the square root of V in the x squared plus V in the y squared, as we saw in projectiles. So in conclusion, an electric charge moving through a uniform electric field follows what we call a parabolic path, or the path is a parabola. And the cathode ray tube is a practical example of the motion of electrons in an electric field in our everyday life. Although the TVs using cathode ray tubes have been phased out, the cathode ray oscilloscopes still exist, and they use applications, or they apply concepts of of charged particles in an electric field. Computer monitors also use the same principles, and of course the ordinary X-ray tubes. Examples as we wind up this. Let's see a few examples. Most of them will be tried by you. So we have seen the path. In conclusion, we have seen that the path for an electric charge is actually a parabola, or it's a parabolic path. Examples: an electron enters an electric field to that we have just seen above, with the horizontal velocity of that. The horizontal length of the plates is that. The electric field strength, that is E, is that. Calculate the vertical displacement of the electron. Calculate the vertical displacement of the electron for the time it is between the plates. So we don't need to quote an expression apart from the equations of motion. Since I don't have enough space, I will use the top part to give you a hint on this. So S is going to be equal to ut plus a half at squared. In the vertical, initial velocity is 0, so it means S is going to be equal to a half times acceleration in the vertical times t squared, if I consider vertical motion. If we consider horizontal motion, we have already seen that the time between the plates is L over V. So this time will simply be L, which is 2.0 times 10 power negative 3, divided by V, which is 7.0 times 10 power 7. That gives us the time between the plates. Then for the acceleration, we have E as this. Electric field strength is equal to the force per unit charge, which is equal to the mass times the acceleration over charge, which means the acceleration in the vertical is going to be E, which is 3.2 times 10 power 5 times the charge. It is an electron, 1.6 times 10 power negative 19, divided by the mass of an electron, which is 9.11 times 10 power negative 31. So we have this, we have the time. All that remains is to substitute. So when I substitute, I'll have S being equal to the value of T, or a half, times acceleration, which is 3.2 times 10 power 5 times 1.6 times 10 power negative 19, divided by 9.11 times 10 power negative 31. Then multiply this by T, which is 2.0 times 10 power negative 13, divided by 7.0 times 10 power 7, but remember this one was squared. And then I just press my calculator to find the final answer. So I have come up with 2.3 times 10 power negative 3 meters. Of course, because it is an electron, the force or the displacement will be vertically upwards. If it was a positively charged particle, the displacement will be vertically downwards. Number 2, by the way, you can verify this answer by your calculator. The vertical deflecting plates in a TV set are 5 centimeters long and 1 centimeter apart. If a PD of 100 volts is applied between the plates and the electron beam enters horizontally midway between the plates with a speed of 2.0 times 10 power negative 7 meters, find kinetic energy gained from the electric field by an electron in the beam. So all we need is the speed with which it emerges from the field. We have the length of the plates. This is the length of the plates. We have the speed with which it enters the field, so we know the time between the plates as this divided by that. As we have seen that example, we have the time between the plates. We need the acceleration to find the speed from v squared equals to u squared. I mean from v equals to u plus at, we shall find the velocity in the vertical. Remember, the velocity in the horizontal does not change. The velocity in the horizontal does not change. So if we can obtain the speed with which it emerges, then we should be able to get the kinetic energy gained from the electric field by considering Ek is equal to a half mv squared. Ek is equal to a half mv squared. I will not go into that. Number 3, a beam of electrons accelerated with a PD 500 then enters a uniform electric field of strength 3.00 times 10 power 3 created by two parallel plates. Now they have given you a PD through which the electron is accelerated before it enters the field. They have given us the PD through which the electrons are accelerated before they enter a uniform field of electric field strength this. That means the 500 would be used to find the initial speed before it enters the field. So that is work done is equal to charge times accelerating PD, which will be equal to a half mv squared. This will give us the speed before the electrons enter the field. So the speed v is going to be equal to 2 times the charge 1.6 times 10 power negative 19 times the accelerating speed, which is 500, divided by the mass of the electron, which is 9.11 times 10 power negative 31 under the square root. This gives us the speed before the electrons entered the uniform electric field. From my calculator, this is 1.3 times 10 power 7 meters per second. That is the speed with which the electrons enter the field. So it is going to be like the initial speed in the horizontal. So they ask you to capture the time that part A was finding that speed, part B the time that each electron spends in the field. Of course, we have now seen, considering horizontal motion, acceleration in the horizontal is 0. The time is going to be length of the plates over this speed here. I think that is obvious. I don't think I need to go into that. Sorry. Let me try to erase here. So you can find the time between the plates, that is the length of the plates divided by V. So the length of the plates has been given as this. So the time between the plates, I'll use the top part since I don't have enough space. The time between the plates is simply equal to 2.00 times 10 power negative 2 divided by the speed, which is 1.3 times 10 power 7. So this is giving me 1.5 times 10 power negative 9 in seconds. So that is the time between the plates. Then the angle theta through which the electrons have been deflected by the time they emerge from the field. So if I try to sketch this, these are the plates. Then the electrons enter, this will be the original path, but then they undergo deflection and they emerge somewhere here. They have a velocity in the horizontal, which is Vx. They have a velocity in the vertical, which is Vy. And we want the angle with which they emerge from the field. So they entered from here with a velocity, which is this. So, of course, as a mathematician or somebody who studied projectiles, you will simply see that tan theta is going to be Vy divided by Vx. You find theta. All we need is Vy. Vx remains the same as this because there is no acceleration in the horizontal. But Vy will change because Vy will be equal to initial velocity in the y, which is obviously 0, plus acceleration in the y, which you can now calculate, then times t, which t we have already found. So your task as an assignment, you'll find a v in the y, substitute in this expression here, and find theta by the tan inverse of this. Vx is the same as the initial velocity. Vx is the same as the initial value of v, which is 1.3 times 10 power 7 meters per second, because there is no acceleration in the horizontal. Vy is the one which will change because there is an acceleration in the horizontal. Note that they have given you that E over m is 1.76 times 10 power 11. So when I'm calculating the acceleration and I see E over m, after all, the force, which is mass times acceleration, is equal to Q times E, or it is equal to E, small e, times capital E. This is small e times capital E. So if I divide by m, so it means acceleration is equal to E over m times E. And E over m has been given, and capital E has also been given. So the acceleration here is going to be 1.76 times 10 power 11, then times E, which has been given as 3.00 times 10 power 3. That will give you the acceleration. That would give you the acceleration. So all you do is to substitute now to find Vy. V in the y is going to be acceleration, which is this times the time. And now we just substitute in the calculator. This is 0. Acceleration in the y is this. Then the time is 1.5 times 10 power negative 19. So V in the y, I'm getting 8.0. I'm getting approximately 8.0 times 10 power 5 meters per second. That is V in the y. Now to find theta, you just go back. Tan theta is Vy over Vx and get the tan inverse. So let me find the tan inverse. Vy is this, Vx is this. Pressing to find the tan inverse. So the angle theta is 3.4 degrees. You can verify that. Okay, so that being said, you have one question that you can try out. This is trial question number 4. A beam of electrons is excited through a potential difference of 200 volts and is directed midway between two horizontal plates, length 5 centimeters and a separation of 2 centimeters. The potential difference across the plates is 80 volts. So it is excited through this before it enters the field. The PD across the plates is this. So do not confuse these 2 volts. This one will give you the initial velocity before it enters the field. And note that the work done is going to be the charge times V, which is equal to a half m v squared. This one will give you the initial velocity V before it enters the field. And this one here will give you the electric field strength. That is, because they said calculate the speed of the electrons as they enter. So you are using this to find V. Explain the motion of the electrons between the plates. Of course, we say they follow a parabolic path. Find the speed of the electrons as they emerge from the region between the plates. In other words, you want to find V resultant, which will be the square root of V in the X plus V in the Y, but these are squared. V in the X will remain the same as the one you have got in part 1. V in the Y will change because of the acceleration. So V in the X is the same as the initial velocity, but V in the Y is the same as initial velocity in the Y plus acceleration in the Y times T. Remember, T is equal to the length of the plates over the initial velocity V because we considered horizontal motion. The velocity you get in part 1 will help you to get the time between the plates. The acceleration in the Y will be got from simply charge times electric field strength divided by m. If E is not given directly, E is V over D. So this will be the same as Q times V over M times D. That will give you the acceleration. The V we use here in finding the acceleration is now this, because this is acceleration within the field. The charge, those are electrons. The mass, those are electrons. Then D is the separation between the plates, which is 2. Initial velocity in the vertical is 0. So you just substitute this. V in the Y will be equal to Q times V over MD times T, which is L over V. Then now we substitute for the values of V in part 1 and V, the second value of V squared, and find the square root. Yeah, for now, let us stop at that point. Next will be electric fields 2, where we look at electric field due to a point charge. See you there. Have a good time.